And so let's talk about that. Let's talk about magnetic fields, because I know that's has a lot to do with the research that you do. And it's not just the study of plasma, it's sort of the behavior of plasma and how it relates with magnetic fields. So maybe introduce us to the SWARM project, which is one of the projects you're a lead on. What is SWARM all about?
So SWARM is a 3-satellite mission that was put together by the European Space Agency, and it was part of a series of satellite missions that go back to the 1960s to study Earth's magnetic field from space. The reason you want to do that is because from orbit, you can build up samples of all of Earth's surface, although from a distance, but you have daily access pole to pole to build up a picture of Earth's magnetic field. Right. And the effect of that magnetic field extends out into space, hundreds of thousands of kilometers. And so SWARM is the most recent mission to make precise measurements of the magnetic fields. But they did something different with SWARM, because the magnetic field is half of a fundamental force. Actually, it's half in physics of what we refer to as the electromagnetic force. Right. So there's electricity and magnetism. They're two sides of the same coin. All the missions up until SWARM looked at magnetic fields. And then when SWARM came along, they realized that we really have to do a good job on the electric fields as well.
I see.
So our involvement at the University of Calgary is to have provided the so-called SWARM electric field instruments.
Got it. Okay. So in some ways it's intended to sort of build on our knowledge of magnetic structures and improve our knowledge of the electric fields.
Yeah, and their interplay. And you really see this interplay outside of Earth's atmosphere. Where you see so inside the Earth is where the main magnetic field is generated. And we see that magnetic field extending out. But also what happens is the Sun-Earth connection generates huge electric currents. And
Right.
when you're inside those currents, you're seeing both the electric and magnetic components at the same time. And that allows you to put together a picture of energy flow, for example.
Right. Well, why don't I put up, I have the announcement. There was a recent announcement of a discovery that was made in partnership with the University of Alberta, University of Calgary, and was ESA part of the announcement as well, or yeah?
They did issue a press release because SWARM is their mission. It's their baby. Yep.
So let me put up I'll do a share screen here of this, the announcement, but in particular, I'll put on the video that is currently on the site, and it shows the SWARM satellite there. Let me see if I can go full screen, if that makes a difference. All right, yeah, so we don't have volume on this video. I think there's some text over top of it. Maybe I'll go right back to the beginning. But this was, I guess perhaps to help illustrate some of the things you were just talking about, David. Mm-hmm. For those who are not familiar with the Sun-Earth relationship, the sun is constantly launching, these charged particles in all directions. Every now and again, there's a blast that's heading towards Earth. And then Earth's magnetic field will respond or I guess react to that impact from incoming charged particles, electrons and protons. So David, what are we looking at here when we see these lines in this structure here?
Those are the lines of the Earth's magnetic field, and they do tend to focus energy into the northern region in a ring we call the auroral oval.
Right.
So the aurora is one consequence of this interaction and exchange of energy. And I might just point out here in the SWARM satellite, you see the white box at the front of the satellite. That's the electric field instrument.
Right.
And on the tail, the boom behind is where the magnetic field detector is. You have to get it away from the spacecraft and all the electrical noise that's on
Let me go back as I try not to massacre this footage here. Here we go. So there we have a look at the satellite itself, and you said there are 3 SWARM satellites.
That's right.
Are they identical?
They're identical.
Okay.
But in different orbits.
And are they following one another? Are 2 of them following each other?
Two of them are flying more or less side by side.
Yeah.
They're all in polar orbits.
Right.
And then the two of them we call Alpha and Charlie are side by side. And that they're meant to pick up gradients, variations in the crustal field of the Earth, east to west.
Okay.
And that's why so you can difference east to west by having them side to side. And then there's another satellite, Bravo, that's in a completely different orbit. And that's with the three, then we can tell if a disturbance, any disturbance that's seen is global through the Sun-Earth connection,
Right.
or something local or regional.
And what inspired the project? Was it that there was a gap in knowledge, or was there a discovery that ESA and U of C and others had been targeting in specific? Like, I think about Themis, for example, which was largely looking at what are the triggers of geomagnetic storms or magnetic reconnection. So
Right.
what was it that was the driver behind Swarm?
Well, it's actually two-pronged, and it's interesting you mentioned Themis, which is a science-focused mission that is a discovery-focused mission. Swarm falls in a different category, which was Earth observing, and that's about understanding our planet in better detail and more accuracy, so that we can use that information for predictions. And so, Swarm was, as I said, one of a series of magnetic field, precision magnetic field measuring satellites. And so that has all kinds of, that's sort of a monitoring problem, and it has all sorts of practical implications. Because the Earth's geomagnetic field is highly structured, and we have to find out, we want to resolve that structure. And more importantly, it's evolving fairly rapidly. So the North Magnetic Pole has moved a couple thousand kilometers in the past few decades, and used to be right smack dab in Canada, and now has reached the pole and is headed the geographic pole, and is heading over to Siberia. So studying the Earth's magnetic field and its fundamentals is part of it. Right. As I mentioned, putting electric fields into that equation was new and discovery driven, and has resulted in many discoveries, given the new knowledge, the new capability we have by combining those two.
Right on. And I remember when that story was the breaking news that Earth's magnetic field was moving, or that the geomagnetic North Pole was moving. And I remember getting interviewed by the Globe and Mail, or being asked for comment on it from Yellowknife's point of view, where aurora tourism has been thriving for so long. And, I thought, well, it's kind of a great outreach opportunity, because for those who don't know, it's a moving target every day. It's not that it's just packed its bags on a Tuesday and left town, but in fact, it was just a trend that it was starting to head towards Russia, or heading out of Canadian waters. And I found it to be an interesting experiment in our understanding of the North Pole, geographic pole versus geomagnetic pole versus the magnetic pole. And then the other element was just at the time, I think Russia was working on claiming the Lomonosov Ridge near Greenland as their own. And I think that was an international discussion about who is the rightful owner of this ridge. And so when the geomagnetic, I think it was the geomagnetic pole that was in the media, maybe it was magnetic. Actually, maybe it was just the magnetic pole that was being talked about in the media, was drifting towards Russia. My comment was, we did such a good job managing it in Canada, I anticipate that it will be back.
Yeah, well, it will in another 500,000 years or so.
That's right. Yeah. And the auroras will be great then. They'll be great from now until then, too.
But, there was one thing we should point out that's really interesting, because the first question that might come to mind, if this magnetic pole has moved 2,000 kilometers, what is it dragging the aurora with it?
Yeah.
And the answer is no.
Oh, tell us more. Tell us more, David.
So certainly not to that degree. And here's why. So the pole that we're talking about, this is known as the dip pole.
Yes.
And its definition is that that's the point where the magnetic field is vertical. So in the northern hemisphere, the magnetic field is pointing straight downward. If you have a compass, compass won't do you any good except to tell you which way is down, basically.
Right.
But as I mentioned, deep within the Earth is where this magnetic field originates. And so it turns out that the dip pole and the structure of the fields around the dip pole are that's sort of a regional thing. It's not global. And that, think of it as a ripple in the magnetic field that doesn't really reach that far out into space. And so the other definition of the pole is what's called the magnetic dipole axis. So think of it just a big bar magnet in the middle of the Earth.
Right.
It creates the classic magnetic field you see in textbooks or wherever. And that doesn't match up with this regional or local perturbation, which is the dip pole. And so the fact that the aurora isn't being pulled away with the dip pole means it's controlled by the internal dipole. It's because that's what we call the lowest order term. It means it's the one that reaches farthest out into space.
Right.
So that's also telling us something about where the aurora is formed, which is further out. And we know more and more. It's many tens of thousands of kilometers away from the Earth. In measurements of Earth radii, which is what we usually use, the aurora starts maybe at around sometimes as close as 6 or 7 Earth radii out, and then it picks up at 8, 9, 10, and beyond. So it's a good fraction of the way toward the moon.
So to bring it down to Earth, though, when we talk about the structures that we see from Earth, we're seeing the illumination of magnetic structures as particles pour into the upper atmosphere. So, for those who are like now thinking that this conversation is, really deep and powerful into the realm of all things invisible, it really actually starts with some of the visible things that we can see from the surface. Like looking just 100 kilometers up on an average night in Yellowknife, there's this green glow that is an arc to start the evening. Then it becomes a little bit more active as the evening moves forward. That's actually giving us an indication of where some of the Earth's dominant magnetic structures are on a vertical axis, basically passing right through the location where a lot of folks are standing in the north. It's not just Yellowknife, of course. It's anyone that's at the same magnetic latitude. But,
Right.
You mentioned earlier, you talk about how the magnetic engine, if you will, is at the core of the Earth, coming outwards from that core and heading out into space. I don't know why I'm pointing up here just to the top of my basement ceiling here. But it reaches out to space. But it's telling us a story when we see that aurora moving there, when we see that's actually a sign that particles are now running into our ionosphere. And now from your point of view, where you're looking at things from above and trying to measure magnetic structures above and thousands of kilometers out, what are some of the things you think of from the surface about the same aurora that we're watching in the north? Like what's going through your mind when you hear we're seeing auroras? Tell us what you're thinking about.
Well, that's one of the very cool things about the auroras, because you showed the graphic earlier of the magnetosphere, this big magnetic bubble, and it is a huge volume of space. And yes, we can send satellites out there, but can you imagine, here's an analogy, trying to map and understand ocean currents with measurements from one ship?
Yeah, good way to put it.
And so you want more ships. How many ships would it take? In the case of the ocean, you have buoys and ships and centuries of measurements. In space, near Earth space even, we're just getting started. And we have a handful of satellites that have the proper instrumentation on them. But so we're just really looking for signs of the source of the aurora. We're looking really for a needle in a massive haystack.